Welcome back to this course on tribology. This is the third lecture, and we'll be discussing today on surface contact. Now, surface contact is a very important issue in tribology because the main problems of tribology are the friction and wear, and both these occur at the surface of contact or at the interface of the two surfaces. Therefore, we need to know what happens at the interface, particularly as far as the deformation of the asperities and the surfaces are concerned. So today we'll be discussing mainly the deformation at the surfaces and how it leads to the problems of friction and wear. Okay, so this picture we have seen many times, but this is important to understand that when the two rough surfaces are in contact, the contact occurs only at the peaks of the asperity, only in the few points. And when we talk about the deformation at the contact, or the two surfaces when they come in contact, deformation doesn't occur on all the points. Deformation first occurs at the peaks of the asperities, and then gradually it comes down to the bulk. So we need to first understand how the deformation progresses as we load the two surfaces from peak down to the bulk of the surface. So this slide shows that we have contact only at the peaks, and obviously the deformations will also be at the peaks initially, peaks, and then the deformation will proceed downward. Now, in order to do that, we take a model, or we consider that instead of two rough surfaces, we take one rigid and flat surface, as shown here, and one rough and deformable surfaces. It is easier to model this rather than two rough surfaces. But if we do that, we have to make one difference in our calculation. That is, when we are bringing two surfaces in contact, surfaces of standard deviation of surface height sigma 1 and standard deviation of sigma 2, then we can replace this contact by this contact of a rigid flat surface and a rough deformable surface with the standard deviation of the rough deformable surface as sigma 1 square plus sigma 2 square to the power half. That means we have a very easy problem now to solve. A flat rigid surface is approaching slowly to the rough deformable surface, and as it approaches, it deforms starting from the top peak, and then it goes downward. And so that's what is shown here. We have a rough deformable surface and a flat rigid surface coming from the top. And here, for example, we have taken a rough deformable surface with a zero normal, zero mean Gaussian probability density. Now, as we go ahead, first thing we need to understand that as the peaks are being deformed, then we need to know what are the shapes of the peak. If you look at this peak, it looks like a very sharp peak. But in reality, the peaks are never sharp like this. They are rounded. And if you look at a real image of a surface, either in a scanning electron microscope or some other, you will see that the surfaces are never like this. This is what is shown in a tally surf or a or some other scanning surface roughness measurement machine, we see this, but the surfaces are never rough, never peaks like this. They are more like this. So here we assume a hemispherical surface. This assumption is not very bad, because if we go to the peaks of the surface, they are more like hemispherical surface, peak. And then we assume that the flat surface is coming slowly and deforming the hemispherical surface. And then initially the point contact becomes circular contact. The projection of this will be a circle. And then we'll prove later on that if the radius of the contact is A, then A squared is 2 or delta, delta being the deformation. We'll see this more later. But for the time being, let us understand this clearly, that instead of having two rough surfaces of standard deviation sigma 1 and sigma 2, we take one rigid flat surface and one rough deformable surface with the standard deviation sigma 1 square plus sigma 2 square to the power half. Okay, with this, we go ahead with the deformation of the single asperity. What we have seen in the last slide can also be represented as a number of hemispheres at different heights, and a flat, rigid, smooth flat is coming from the top and deforming. So as it is going down, it is first deforming the top hemisphere and then going on to the second and third and maybe more and more. So this is the picture that we use for modeling the deformation of the asperities. Asperities are nothing but the peaks. If you do not know peaks of the surfaces, asperity deformation. Now, if we look at one of the peaks upside down like this, as I was saying in the last slide, that the flat surface will have a point contact initially, and it will go on to have a larger contact, and the contact area will be a circle. Let's say that the radius of contact is A, and the radius of the hemisphere is R, and the load is W, and we move this, move either the deformable surface or the flat surface. This is what the tribology is. We have got two surfaces loaded, and one of the surfaces or both the surfaces move with different velocities. So here I have shown a deformable hemisphere loaded with a force W against a flat surface, flat rigid surface, and it's making a radius and circular contact of radius R. So with this in our mind, we go ahead to have more modeling. Now, before we go to the modeling, it is important to understand that when two circular bodies are brought in contact with a load applied onto them, just as shown here, two circular bodies, then there is a large localized stresses are developed. And this is a typical example or typical much quoted picture which shows that the stresses are developed here. This is a photoelasticity picture. Photoelasticity is a method of finding out the stress distribution at the contact or at any loaded body. So this shows the stresses developed at the contact, and this tells us that when the two curved bodies are brought into contact, then initially there will be a point contact, and then it will grow to a larger contact area. Let's take two marbles and bring them in contact under some pressure. So the contact will be at a point. Nevertheless, even if you increase the load, the contact will never increase. But take two rubber balls and bring them in contact, then press them. You will see that the contact is increasing. Initially, from initial point contact, it will increase. And this is because of the elasticity. If you take two rigid bodies, they will not increase because the contact is not deformable. So this is the main cause of deformation. And with elastic contact, it produces stresses, and this is known as Hertz contact. Hertz contact is a very major issue in tribology and in many other machine part analysis. Henry Hertz solves this problem of stress distribution long back in 1882, and one of the very well-known book written by Professor Hale Johnson of Cambridge is 100 Years of Hertz Contact. In fact, this Hertz contact theory or the contact mechanics has in a way revolutionized our understanding of contact mechanics. And we now can find out many important parameters that we couldn't do before. So Hertz contact is an important milestone in our tribological understanding. Now let's go ahead and see how we use this Hertz contact. There are many applications of Hertz contact in machinery and in daily life, like ball or roller bearings, gears, sliders, rollers, and there are many other applications. And they may all be broadly classified into the following groups. One sphere upon a sphere, sphere on a flat plate, sphere on a cup. This is a typical contact of a ball bearing with a race. Bearing, in ball bearing, balls are in contact with a curved race. Similarly, we can have a typical contact of cylinder on cylinder, cylinder on a flat plate, cylinder on a curved cylinder. These are all examples that may be fitting to replace the typical machinery problems, like this will be applied to the roller bearing, and this will be applied to the ball bearing, and so on and so forth. So these are the typical examples of many contact problems that we often face and try to analyze. So with this, we need to go ahead and see how we can analyze this. As we say that when the smooth flat surface comes down from the top, then it deforms the top or the topmost peak. And let's take one asperity at a time. So we take a single asperity. Asperity, as we have said, will be assumed as a hemispherical surface or hemispherical body, and it is in contact with a flat surface. So when we apply a load P, for example, then from the initial point contact, it goes up and makes a contact area of 2A. It will be a circular contact area, and its radius will be A. So if we look at this triangle here, then if we try to find out delta is the deformation. So delta is this. So delta is nothing but this is the radius minus this distance. Now this distance is nothing but r square minus a square. So that's what I write here. R is the radius. This is the radius. R minus r square minus a square. A is this to the power half. That will be equal to r minus r. We take the r out, and 1 minus a square by r square to the power half. If we expand this binomially and take only the first term, then it approximately comes down to this, half a square by r. So that means that the contact radius of the deformed surface A can be given related to the radius and the deformation as a square is equal to 2r delta. So that is from geometry, very clear, and no problem there. But for analysis, in many cases, we use an empirical relation which says a square is approximately equal to r delta. So the contact area is pi a square, obviously this contact area, which is a circle, pi a square, so it is pi r delta. Now the rest of the derivation will not go into it, and it can be looked into a very well-known book written by Timoshenko and Goodyear, and it is called Theory of Plasticity. And there it can be simply, it has been shown very clearly that under the elastic deformation, the Hertz theory says that the load P here is equal to 4/3 E dash R to the power half and delta to the power 3/2. Now let us not go into the derivation. It is a simple derivation, but I'm not going into the derivation. But let us understand the equation. A is the contact radius. So here A is the contact radius, and it is pi r delta. And R is the radius of the asperity. So this is the asperity. So it is the radius of the asperity. P is the load, and E dash is the equivalent elasticity. We have got two surfaces. One is the asperity, hemispherical asperity, and let's say its elastic constants are E1 and μ1, elastic modulus and Poisson's ratio. And let's take the two elastic constants for the flat surface as E2 and μ2. E2 is the elastic modulus and μ2 is the Poisson's ratio of the second body. Now, this can be combined together to give a equivalent elastic modulus, which is 1 by E dash equal to 1 minus μ1 square by E1 plus 1 minus μ2 square by E2. And this is very simple, and it can be shown during derivation that it comes out like this. And it is necessary to do this because we have shown earlier, I'll just go back a few slides back here, we have converted the two surfaces into one deformable surface and one rigid flat surface. Now this deformable surface has a standard deviation of sigma 1 square plus sigma 2 square to the power half, but it also needs we also need to know the elastic constants. And the elastic constants given like this. Elastic constant is 1 by E dash equal to 1 minus nu 1 square by E1 plus 1 minus nu 2 square by E2. Okay, so we'll go ahead with this, that we have got on one deformable asperity in contact with a rigid body, and the deformation of the asperity is a circular, gives a circular contact with a radius A given by whose contact area is given by pi r delta, delta being the deformation, and it has got a equivalent elasticity of E dash, and the load is given by 4/3 E dash r to the power half delta to the power 3/2. Remember this will be used later on for further derivation. So this is a very useful, these two are very useful equation for our further analysis. Okay, so in this slide we simply take help of the Hertz analysis and show that the contact area of a single asperity against a flat surface is given by pi r delta, and the load P, we may know the load P, but this can be expressed in terms of the other variables, will be 4/3 E dash r to the power half delta to the power 3/2. So with this, we go ahead with the further derivation or further analysis. Now, in Hertz contact, there are few more parameters we need to know. As I say, when the two spherical surfaces or any other curved surface, not necessarily spherical, any other curved surfaces come in contact, then the Hertz analysis will be applicable. And we can, without going into the derivation, we can make use of the Hertz analysis and say that the maximum pressure that occurs at the contact is P max is 3/2 P by pi a square. So it is 1.5 times the nominal pressure. The nominal pressure, one would expect P by area. Area is pi a square. But it is a bit more than that. In Hertz contact, the contact pressure, maximum contact pressure, is 3/2 P by pi a square. In fact, the contact pressure is semi-elliptical in nature. I'm not going into the details of this. And the peak point or the maximum pressure at the contact is given by 3/2 P by pi a square. And the delta, which is the deformation, as we press the two curved bodies or two deformable bodies, for example, in this case, the one would penetrate into another. Suppose you take a rubber ball penetrating onto a steel ball, then the penetration will be delta. And this delta is given by Hertz theory, a square by r. A square by r comes from our previous understanding that a squared is r delta. So delta is a square by r. This we have seen before. And this has been shown by Hertz to be cube root of 9 p square by 16 e dash square r. This is a very important equation. Needs to know for any tribological analysis. And area of contact, area of contact or radius of contact, A, here, 2a is the diameter. Area of contact A is cube root of 3pr 4e dash. Now here, let us look at it very carefully. As we said, the equivalent modulus E dash is given by 1 by E dash, 1 minus nu1 square by E1 plus 1 minus nu2 square by E2. This we have seen before. But here we have introduced one more equivalent radius. If we replace this by a curved body and a flat plate, then it will have a equivalent radius of 1 by R, 1 by R1 plus 1 by R2. So these, in this equation, we write the equivalent elastic modulus and equivalent radius. Okay, so these two equations are very important in any tribological analysis, and we'll see that later on. Say we want to find out the stresses developed in the ball bearing contact, then we need to know these three parameters, and then we can go ahead further with this. Okay, so we use this Hertz contact theory, and the derivation can be obtained in the theory of elasticity by Timoshenko and Goudia. Derivation is not very difficult. What is done there is that you take 2 points on the surface of the curved body, say this and this, and as the surfaces are pressed and the points come together, at some load, the 2 points will be 1, and hence then the distance will be reduced to 0. But as we press together, there is a deformation at this point, but at the same time, there is an approach. The 2 points are approaching together. If you deform 2, say, rubber balls, points away from the contact are deforming as well as approaching. And using this very elegantly, Hertz has shown that this kind of this type of expressions come. The derivation is very simple, but it has a fundamental elastic understanding. Okay, so with this, we in this slide we learned that when the two spherical bodies are in contact, or any two curved surfaces are in contact, then the maximum pressure is given by 1.5 times the nominal pressure P by pi a square, A being the radius of contact, and delta, the deformation, is given by cube root of 9p square by 16 E dash square R, E dash being the equivalent radius and R being the equivalent, E dash being the equivalent modulus and R being the equivalent radius. And A, the contact radius, is given by the cube root of 3pr by 4 E dash. Again here, R is the equivalent radius and E dash is the equivalent elastic modulus. Okay, now with this, remember that this analysis that we have done now is for single asperity. But now, we can have a problem of two cylinders coming into contact. This thing happens in roller bearing. The previous example is applicable to ball bearings, but for roller bearing, we need this kind of configuration. There also the Hertz theory has predicted that the contact, half the contact, when the two rollers are in contact, the contact area is initially a line, and then it goes to a rectangle. The rectangle, we say that the width of the rectangle is 2b, and the length is the length of the roller. So the half the width of contact, b, is given by 4pr. P is the load, r is the equivalent radius, and pi l E dash. L is the length, and E dash is the equivalent elastic modulus. Here again, the maximum pressure, not stress, maximum pressure that is developed here during loading, P max is given by 2P by pi BL. So these two equations are also very useful in analysis of ball and roller bearings. Now we go on to the deformation of a real surface, where there is not only one asperity, there are many asperities, and the surface is coming from top and making contact with the topmost asperity and going down and down and making contact with many more asperities, and deformation is proceeding until it totally gets flat. So we now look at the problem from the distribution point of view. So if you want to find out the number of asperities that is being that is coming into contact at any given point. So as it is coming down, and this is the mean line, suppose we say that the distance between the flat plate and the mean line is D, and the distance of the highest point peak, or any point for that matter, is Z, and delta is the deformation. Then the number of asperities that comes into contact at any given distance or at any given position of the flat plate D will be given by N, given by capital N. Capital N is the total number of asperities per unit area, integrated the probability density function, Pz. This we have discussed in the earlier class. So the probability density function has to be brought in, and we integrate this between D and infinity. Why infinity? Because we assume that the asperity can be very high, and as the flat is coming down, it is coming down from infinite distance. I mean, this is a relatively high distance compared to D. So we integrate this probability density function between D and infinity, and with N as the being the total number of asperities per unit area. So as it comes down at any given point, the total number of asperities that are in contact will be N integral D to infinity Pz dz. Okay, and this is important. But here we'll see later that there is a problem here. The problem is that at any given point, we can measure Z, because that we know, the topmost point. And we can also measure delta, because we can see how much it has deformed. But D is a difficult parameter to measure, because as it is going down, it's a variable that is difficult to measure. So we'll keep it at this point with the D to infinity, and we'll see later how to get rid of this. Now let's come to the area of contact. Now, area of contact for a single asperity, as we have said before, is pi a square. And hence, we have taken empirically that a squared is r delta. So it is pi r delta. So the real contact area again is the contact area between the flat plate and the rough surface. So that depends on how many asperities it has deformed and to what extent it has deformed. So there, again, we take the area for a single asperity and integrate it with the probability density function Pz dz. But here, delta is replaced by Z minus D, because delta is not our variable is Z. So we replace delta by Z minus D. So the real area of contact, which is an important issue as we have seen before, can be calculated by taking n integral d to infinity pi r z minus d pz dz. N because number of asperities has to be taken care of. And this is the total dispersion of the asperity area. Okay, so from single asperity to multi-asperity, we simply integrate this with respect to Z and including the probability density function Pz dz. Similarly, the load that is applied, we know, but that can be expressed in terms of the other variables. For single asperity, as we have seen before, is 4/3 E dash R half delta 1/3 and delta 2/3 delta delta 3/2. So this is P is equal to 4/3 E dash R half delta 3/2. And here we do the same thing, but we integrate with probability density function and dz. So E dash R half delta is replaced by Z minus D to the power 3/2 and Pz dz. So this gives us the total load. So this is a slide that tells you how we can find out the total contact area, total number of asperities in contact, and the total load at any given point of loading. As the loading goes down and down, this D will change, and hence our integral value will be different. One interesting point to note is that if you integrate this from minus infinity to plus infinity, then you get the total number of asperities, as we have seen before. So this will be 1, and hence it will be number of asperities in contact will be the total number of asperities. And the same thing will happen here. So there it's a little difficult to understand, because as we are going from minus infinity to plus infinity, it is going inside the bulk of the material. Below the lowest valley, you have no undulation of surface. So you have got the bulk of the material. So the total contact area will be simply the area of the two surfaces. And similarly, the load will also be increased. Anyway, for the time being, let us understand that for any given loading condition, this integral will be in terms of d to infinity. So this tells us how to convert the parameters like number of asperities in contact, real contact area, and total load from single asperity to multi-asperity. Okay. Now, let's say that we said Pz. Now, or Py in this case, we can write Py or Pz. Pz or Py is a distribution. Now, what is this distribution with reference to an engineering surface? With regard to engineering surfaces, normally they are taken as Gaussian distribution depending on how they're machined. If they are machined by grinding wheel, then they are usually random rough surface. Otherwise, it will be sinusoidal bond or cosine sine. But normally, if we take a rough surface, a random rough surface, then the top few percentage of the asperities will have a exponential distribution. It is easy to use this to understand what happens in the deformation process. If we use this exponential distribution, then we can analytically solve the previous equations. If we put this exponential distribution here, here, and here, and then we can, it is simple, we can analytically solve this, and we can show that the total number of asperity in contact is n into exponential to the power minus d by sigma, sigma being the standard deviation of the equivalent surface, and area is n number of asperities in contact, pi r sigma. There is a very interesting conclusion about this. I'll come to that later on. And the load is n pi half E dash R half sigma to the power 3 by 2. Now this, combining this A and P equation, we can write P as A by root sigma E dash by R to the power half. Now this is a very important derivation. Why? Because it shows that the load is proportional to the number of contact spots and contact area. If you remember, when we started discussing the tribology, concept of tribology, we said that the real area and the apparent area. So the real area will obviously depend on how much load we have put, and it will not be same as the apparent area. And it will be proportional to the load. Load will be proportional to the how many asperities it has deformed and to what extent. And hence, it will be proportional to number of contact and contact spots and the contact area. So this is very important, because then we can say that when two surfaces are in contact, the load is not deforming the whole body. It is deforming only the top few asperities, depending on how much load you are putting. Again, coming back to the example of duster and board, if you apply with the wooden side on the table, if you apply a load, say few grams, then only few asperities will be deformed, and that deformation will be proportional to the load. Unless you apply a very heavy load, then the deformation is so much that all the asperities are deformed, and then this concept does not work. Then the apparent area and the real area is same. So it is important to understand here that the load decides how many asperities will be deformed and what is the contact area. And the contact area, as we discussed before, may or may not be same as the apparent area. In fact, in most cases, it will not be the same as the apparent area. And this is analytically proved using, of course, the Hertz contact mechanics theorems, that the load is proportional to the number of contact and the contact area. Now this was simple because it is easy to integrate. It is easy to integrate these equations with the exponential distribution, which is simply 1 by sigma e to the power minus y by sigma or z by sigma. This is a simple integral, and we can do it analytically, and that's why it was easy to get these expressions. But when we take a Gaussian distribution, then which is p y or pz 1 by 2 root 2 pi sigma e to the power minus y square by 2 sigma square. This is a typical expression for Gaussian distribution. Then the integration becomes difficult. And obviously, it cannot be done simply analytically. So there we need to use numerical methods to solve it. Now this was done by Greenwood and Williamson long back in 1966. And they have shown that the same conclusion applies even for Gaussian distribution. We have previously seen that this applies for the exponential distribution, but here we see that it applies for the Gaussian distribution also. So they have concluded that for elastic contacts of two rough surfaces, the contact area depends on load. And not only that, when the two surfaces are in contact, two rough surfaces are in contact, we really do not know whether they are in elastic contact or plastic contact. Because when we have two curved bodies or spherical bodies in contact, we can say whether they are elastic or plastic depending on the load and the material parameters, because that's easy. We can plot the deformation or the load against the deformation, and we can see where it deviates, and we can say that whether it is elastic or plastic. So that will depend on load. But if it is the two rough surfaces, I think try to understand this. If there are two rough surfaces in contact, it is difficult to say whether they are in elastic contact or plastic contact. But Greenwood and Williamson has shown that there is a parameter called plasticity index. In fact, they brought this up and they have found out this, given by E dash by H. E dash is the equivalent elasticity and H is the hardness, and sigma is the standard deviation and R is the equivalent radius to the power half. So this is the plasticity index defined by Greenwood and Williamson. And if this value is less than 0.6, then it is elastic contact. And if it is more, then it is plastic contact. This is a wonderful way of solving a big problem. Because when two rough surfaces are in contact, we do not really know whether they're elastic or plastic. And depending on that, many problems can be solved. If it is plastic, then we know that the surfaces will not regain, and hence the contact will remain where it is. But if it is elastic, there will be recovery, and the loading can be reduced or increased depending on what we want. So it is a wonderful contribution by Williamson and Greenwood and Williamson to decide whether the contact between the two rough surfaces is elastic or plastic depending on this plasticity index. Now, further than that, they have also found out from their numerical analysis that the mean pressure means the pressure at the different asperities will be different. But we can have a mean pressure. Mean pressure is proportional to the contact area, or contact area is proportional to the mean area, mean pressure. And the contact area is proportional to load. So this is a very important conclusion. For elastic contacts, we know that for plastic contacts, we know that the contact will be proportional to load, contact area, because load is area times hardness for plastic contact. Area times hardness. So there, contact area is proportional to load, no problem. And also, contact area is proportional to mean pressure. Mean pressure is hardness here. So for plastic contact, we have this very clearly. But for elastic contact, it was a very difficult thing to decide. In fact, in 50s and 60s, this was a very big issue in the tribological sphere, and where they were trying to understand what happens in the elastic contact, in the elastic rough surface, contact between the two elastic rough surfaces. And Greenwood and Williamson model simply resolved this problem, and they have come up with the conclusion that the contact area is proportional to load, which is same as what we have for plastic contact, and contact area is proportional to the mean pressure also. So these two were very useful thing to understand, but it is not so easy to intuitively say that the surfaces will be elastic or plastic, or the load will be proportional to contact area or not. So this was resolved by, firstly, the use of Hertz theorem, Hertz theory, and secondly, Greenwood and Williamson's model. In fact, there have been many more models and extension of Greenwood and Williamson's model, and there are very different theories coming up. But this remains the basis for all the further analysis, that for both elastic and plastic contact, the contact area is proportional to load, and the contact area is proportional to mean area. So this was a good understanding, but in order to do that, we had to understand Hertz theory and Greenwood and Williamson model. But having said that, let us understand that there is nothing which is absolutely, there is no material which is absolutely plastic or absolutely elastic. They are always elastoplastic. So when we say that the two surfaces are, when they are coming into contact, or in elastic contact or in plastic contact, I think we have to be a little careful, because all the asperities may not be plastically deformed or elastically deformed. Some of the asperities will be elastically deformed, some will be plastically deformed. And hence, the deformation pattern has to be a combination of elastic part of the asperity deformation and plastic part of the asperity deformation. And there have been many theories and investigations carried on this respect. but this is a simple way I like to present this, that we cannot categorically say that when the two surfaces are coming into contact, this contact is elastic, this contact is plastic, because no material is absolutely plastic and absolutely elastic, and hence some asperities will be elastically deformed, some will be plastically deformed, and hence the combination has to be, the total load or total deformation has to be taken care of by the distribution of the two sets of, or maybe more sets of, sets of asperities. We can divide them into elastically deformed asperity, plastically deformed asperity, and also elastoplastically deformed asperity. Many work has been done, but in this simple course, we're not going into this detail, but there are more papers if you would like to go into the detail. So we'll finish it here today, and we'll go on to some other topic in the next class.